Welcome to Modern Physics Lab number 4, Spring Mass System. So our problem is that we need to predict the motion of a spring mass system in which the mass swings in an arc while oscillating on a spring. Our fundamental physics concepts here will be Newton's second law, to which we'll use to predict the position, and where our system will be our spring and our mass, and our surroundings will be the Earth. And then the energy principle, in which we will use to find out insights about energy transfer. And in this case, our system will be our spring and mass plus the Earth. Some major assumptions we make are that our net force is equal to the force of gravity plus spring force. And we're going to use all of this to build a computational model and answer a couple questions. So again, the fundamental physics principles, you have Newton's second law, which, just like all the other videos, says that the final velocity is equal to net force divided by the mass times delta t plus the initial velocity. And then you have the energy principle, which basically states that the change in energy, or the total of all energy transfers, will be equal to the change in the total kinetic energy, and then in our case, plus the change in the potential spring energy, plus the change in potential gravitational energy. And all of this is going to be equal to 0, because for the system that we chose, there are no surroundings. And again, also keep in mind that we will be looking at our position as well. So here are axes and our origin. Our origin point is right here. Again, this is a screenshot from the tracker video. Note your positive y is in this direction, negative y in this direction, positive x in this direction, negative x in this direction. Note here that our mass, so this is the mass of our spring mass system, it does not start at the origin. So some initial conditions, I'm not going to go through all of these. You can pause the video here if you need to, but just to highlight a few. Again, the ball's position does not start at the origin. The ball's initial velocity is 0 meters per second squared. Our time is 0. We will be putting all of our information into the CSV file, and our delta t is 1 over 210 seconds. This data right here, all these initial conditions, are used to get the data we need to make our spring force, or to model our spring force. Again, here, this is just a computational model, so this is how we build our kinetic energy, our gravitational potential energy, our spring potential energy, our spring potential energy. And again, just like we've done in the past, this is how we get our gravity vector, our spring force vector. We add both of these together to get our net force. We update the velocity, and we use that to update the position. Very, very similar to what we've done before. So let's actually talk about our predicted motion versus our observed motion. So in blue you have the predicted motion, and in red you have the observed motion. So notice that they're pretty close. However, we do have a little bit of error, and this is probably due to our difficulty to ascertain the mass of the object while it was oscillating. So if you notice, this is another look at the model that given to us from VPython. Note here that this black arrow represents a constant a constant force of gravity, whereas this blue arrow actually represents a changing force of our spring, or spring force. So the blue arrow was actually changing, the magnitude of blue arrow was changing, whereas the black arrow was constant. So what does this all mean? For our model, is the energy principle satisfied? Well, yes. So this is actually satisfied because when we graph all of our energies, our change in energies, we see that here our delta k, which is the blue, our delta us, our delta ug, all this, you can see the corresponding colors, boom, boom, boom. When you add them all together, this gives us our total change in energy, and that equals this yellow line. And notice how the yellow line stays constant, which is exactly what our last, or what our energy principle says. Another question. How do the x position oscillations compare with the y position oscillations? So when you go to Tracker, our video tracking software, and get the data for the X oscillations pictured here and the Y oscillations pictured here, you notice that the total period, or the period between the oscillations is about 0.605 seconds for the X oscillations and about 0.8 seconds for the Y oscillations. So what this means is that the horizontal period is less than the vertical period, and that our mass has more displacement than Y displacement overall. And that's our video.